Welcome, ladies and gentlemen. He introduced Mary here with our presentation. I first met Mary in Surveying as a rep. She sat over on the right of me, her left front of the classroom. She never stopped talking. That has not changed. When she came to me with this project, I looked at it and I was like, it's truly a small world. A dozen years ago, maybe 15, Hasty Mattern and Mattern on behalf of CSX asked me to take a look at an underground collapsed railroad tunnel just north of this site. And it still entombs a train and 2 people. Fascinating project, subsidence. But it was then I saw first the unique groundwater regime and the water aspects of this site. When she brought this to me, I thought, it is a small world again, and we're coming full circle. One adjacent site to the next. It's a wonderful project. Cities struggle with this type of infrastructure. We're going to see a lot of change in this. Many of your futures will be in this area. She's done an amazing job with software that's complex, and I'm very pleased with it. She's come a long way. She was good to begin with. She's even better now. Thank you.
Okay, as he said, my name is Mary Jaraneski. I'm a civil engineering major. And before I want to get started, I would like to thank my advisor, Doc Rogers, as well as Cat Brewster, the department head, and all the civil engineering faculty, and everybody who showed up today to see what's going to happen. So my project was essentially about trying to figure out how Shaka Bottom, a neighborhood in Richmond, Virginia, could be made more resilient and increase the value of its stormwater design. Shaka Bottom has long been associated with major issues regarding stormwater. So my interest in this project stems from the fact that I grew up around the water. I grew up sailing, I grew up rowing, I grew up playing with fish. But this middle picture is actually from a trip that I went on with the James River Association, and that was an 8-day canoe trip in the summer after 9th grade. And that was where I really became passionate about the environmental protection aspect of being on the water and wanting to help reduce pollution and protect the waterways that I grew up on. So my area of interest, Shaka Bottom, it's a weird name, and it comes from the Powhatan word for flat rock. It's the lowest point in Richmond, and there's also a creek that was paved over called Shaka Creek that runs adjacent and kind of along that 64 pathway as shown. Shaka Bottom also is known for its African American heritage. Shaka Bottom had the largest slave trade between, or the second largest slave trade between 1830 and 1865. And for that reason, there is a lot of activism regarding revitalization efforts within the area in order to make it a respectful change. The streetscape, the way that the streets run is actually the exact same as it was in the 1800s, which is part of why a traditional gray approach of building bigger tunnels and bigger pipes isn't exactly feasible. It's because this is the same as it was in the 1800s. And so this is a close-up of my area of interest, and it's about 50 acres. Originally, I was aiming to do the entirety of Shaka Bottom, but that was too large for me, and it made some of my assumptions kind of not as valid. So this is a picture of Shaka Bottom in 2004. And so this picture is from Hurricane Gaston. It wasn't a particularly large hurricane, but because of the situation within Shaka Bottom and how it responds to floodwaters, it caused massive damage. 5 people were actually killed in Virginia due to this hurricane. And buildings were collapsed, and Shaka Bottom got shut down. 20 blocks of it got shut down because of this, and so that Richmond could respond. Now, a flood wall has been built to help keep rising river levels at bay, and Shaka Bottom has started to rebound. However, there are still major property damage payments being doled out in combined sewer outfalls. So a combined sewer is one sewer that is supposed to carry both stormwater and sewage water flows. During dry weather conditions, this isn't a problem. The sewers are more than large enough to convey this sewage. However, during wet weather, these sewers overfill capacity, and that slurry of a mixture of polluted stormwater and sewage runs off and dumps into the river. And so this is a large problem, and the one that I'm talking about is triggered by a storm intensity of only 1.32 inches per hour. That's not a big storm. So this is a graph showing all of the E. coli tests that were conducted by the James River Association between over the past few years. So that glowing green line, that's the state regulations in order for it to be considered safe. And this is a test site for Rockets Landing, which is a little ways downstream from this Shockoe Bottom outfall that I've been talking about. So this is directly related to wet weather events. As you can see, this isn't mildly above the pass rate. This is, in some cases, like, that was almost a 3,000, the pass rate's 235. That's a humongous spike. And this is E. coli, which in and of itself can cause infections, can cause disease, but it's also a trigger for more infectious and more dangerous bacteria that could be living in the water. So the future of Shockoe Bottom, in particular, right now, is a really hot topic, especially in Richmond. Recently, Richmond was actually selected to be a part of the Rose Institute for Urban Planning, one of their 4 cities to receive urban design assistance. And so because of that, Mayor Stoney, the current mayor, wants to focus on Shockoe Bottom. In the past, a plan was proposed in 2011 to create a baseball arena, but that was quickly shot down because of it didn't seem like the right fit for an area so heavily associated with African American heritage. They were planning on building it directly over the slave trade site, so that got shot down pretty fast. So now Mayor Stoney is working with the Rose Institute to create this revitalization plan, and they've pledged $1.4 billion to revitalize all of Richmond. But Mayor Stoney wants to focus on Shockoe Bottom, saying that he wants to promote growth and opportunities given environmental challenges. So these environmental challenges are what I am trying to address. I think that using green infrastructure, we can flip the discussion about these environmental challenges, this stormwater issue, on its head, and talk about making green infrastructure an asset to the community as opposed to something that nobody talks about, that's hidden, that isn't of value. So my first step in doing this was to calculate the current hydrologic conditions. And so this is my area of interest. As I said, it's about 50 acres. In pink, you can see I outlined all of the rooftops, and then in green are the treetops, and in teal, you can see the miscellaneous green areas. If you don't see teal, it's because there's not very much green. So everyone, guess in your head what percentage of area right now is impervious. So what percentage is asphalt, rooftop, sidewalks, and keep that in your head. This is a close-up of one of the blocks. As you can see, there's one tree for this entire block. The rest of it's gray. And that means that almost all of this water that falls on here is going to go directly into the storm system or run off into the James. So 95%. 95% of this area is impervious, and that's a really, really high number. Traditionally, what you would assume for a commercial area is approximately 85%, and that difference in 10% means that it's going to take a lot less time for water to travel into the storm sewers, and it's going to hit the storm sewer at a greater intensity than it would if it was going over gravel or grass. So I used the watershed lag method to determine the time of concentration, and that led me for a 25-year storm. So a storm that occurs likely once in every 25 years is going to result in a flow of 232 cubic feet per second. So in this room, that would be every 30 seconds, it's going to get right about your head. So you'd be underwater sitting down in 30 seconds. And then in 90 seconds, this whole room would be filled and emptied out again. And that's a lot of water. However, the storm that I'm looking at, for the purposes of hold between 50 and 55% of the rain that falls on it for a storm varying in intensity from 1 to 2.5 inches per hour. And so this led me to help me figure out and estimate my storage that I could create within this area of interest using these tools. I also use downspout disconnection, which just is disconnecting the gutters around the house from going directly into the storm system and having them flow over a lawn or grass or really even just the pavement, as well as rainwater harvesting. It's exactly what it sounds like. You get a big bucket and the rain falls in it. It's a little bit more complicated than that, but not by much. So this is a close-up of one of the blocks within this area of interest. The red shows a green roof, and this green roof is approximately 32,000 square feet, and is estimated to hold for a 1.32 inches per hour intensity storm, 1,500 gallons. The light blue is rainwater harvesting, and then the neon green trees, the little boxes, those are the tree boxes, and those are estimated to hold, all 7 of them together, holds about 800 gallons. And then that dark blue area, that's a rain garden, that's about 150 square feet, and that also holds about 800 gallons. So all in all, not including the rainwater harvesting, this design for this block holds alone 3,000 gallons of water per storm. So this is the whole thing. And so not discussed in the close-up that I showed you was the permeable pavement. The permeable pavement was, for me, something that I tried to utilize really heavily. I was restricted because of the slope of the area. Permeable pavement works best on a flatter landscape, so I tried to keep it where there wasn't as much of a change in slope. I also tried to use green roofs pretty heavily. The thing about green roofs is that you get a pretty high return on investment. Green roofs are more expensive than traditional roofs at a difference in cost of about $12 per square foot, but you replace them a lot less, and so their lifespan is greatly increased, and there's also other benefits associated with it, like a reduction in cooling and heating costs because of the extra insulation. So totally, this design I estimated to cost $3 million. In order to store 335,000 gallons of water for a given storm. However, the storage of the design isn't everything. So I also discussed delaying the water. So by using the curve number method, I changed the infiltratability of the area from a really high curve number indicating low infiltration rates to a slightly lower number. So I got it from 98 for the entire thing down to 91.2. And so that change doesn't seem like a massive amount. However, it does result in a very large change in the water that flows off. So originally, using the curve number method, 1.5 million gallons of water was generated per hour given this 1.32 inches per hour storm from the entire area. Using the adjusted curve number, I reduced it to 800,000 gallons of water. And that change in flow goes from 57 cubic feet per second down to 31.4 cubic feet per second, which is a pretty sizable reduction. And you end up saving almost half of the water. Overall, using this, the reduction leads me to my original cost of like $2.6 million, equals out to $3.74 per gallon of water having so many trees and plants around decreases the urban heat island effect because the transpiration cools down the air, and so that way you're not having to pay for air conditioning so much during the summer months. And there's also various economic benefits of having green infrastructure. So as they say, if you build it, they will come. By creating an environment in which people feel comfortable, people are cool, it's clean, people are more likely to want to spend time there. And that means they're more likely to spend their money. So by